Hi everybody, this is Cal with section 11.1, open and closed sets in R, and section 11.2, which is called, I think, compact sets or something like that. We'll get there. The material in chapter 11 is going to be a bit of a shift from what we've been doing so far. We're going to basically study here what's called point set topology, and this is a soft introduction to some things that you're going to see in 302 and onward. So, we start at the bottom of page 326 with the definition of a neighborhood. We already know the definition of an epsilon neighborhood, and this is just a slightly more general definition. We use that definition to define at the top of 327 the notion of open and closed sets. These are extraordinarily important definitions. You want to really make sure that you know what they mean. And I would work very carefully through the examples in 11.1.3 to get a sense of what sorts of sets are open and what sorts of sets are closed. The remark here in the middle of page 327 under the example is pretty important. This is noting that there are some sets that are both open and closed, and there are some sets that are neither open nor closed. And so open and closed for sets does not work like open and closed for doors and windows. You don't have to be one or the other. You can be both. You can be neither. We have properties about unions and intersections of open and closed sets. So 11.1.4 is pretty important. The union of an arbitrary collection of open subsets is open. The intersection of a finite collection of open subsets in R is open. And there are closed set properties as well. An arbitrary intersection of closed sets is closed. A finite union of closed sets is closed. You should think about what would be counterexamples. Well, okay, that's actually covered in 11.1.6. Why do we need to say finite instead of arbitrary for some of these things? 11.1.6 gives you the answers to those. We get into the characterization of closed sets, so 11.1.7 is very important. And you should think in the middle of the page, after it proves this theorem, it says what this means in terms of cluster points. And so one way to view a closed set is it's a set that contains all of its cluster points. And this is usually a pretty healthy way to think of closed sets. Then we get into characterization of open sets. The idea is that, if we're allowed to have infinite unions of open sets, and this gives us open sets, open sets could potentially be really exotic, and it turns out that this is not the case. A subset of R is open if and only if it is the union of countably many disjoint open intervals in R, so it can't get too bad. After that proof, you should read the little blurb here in the middle bottom of 330. And then we get into a discussion of the Cantor set, which is just really cool. I'm not going to say that this is going to be a major topic for us or anything, but do read the section on the Cantor set. It's pretty super awesome. And your book goes into some cool properties that the Cantor set has. I would read through this and try to follow through it. And that kind of ties together section 11.1. Moving on to 11.2, compact sets. Compact sets are a special kind of set that is not going to seem so terribly important in this class, but it's going to be a very important idea in 302 and in the future. So we're going to define compact sets with a kind of weird definition, and we're going to have a theorem called the Heine-Borel theorem at the end of the section that characterizes what compact sets in R look like. So we start by defining an open cover. An open cover of a set A is just a collection of open sets that, their union contains A. So you can kind of think of, if an open set kind of looks like a little open ball, you can cover your set A with a collection of these little open balls. Okay. Um, your book talks about a subcover and a finite subcover, and these are both really important um, notions for the definition of compact sets. And so make sure you understand 11.2.1 and the associated definitions. Moving forward, your book defines a compact set. A subset of R is compact if every open cover of K has a finite subcover. And I would work through, I would read through these comments pretty carefully, and I would work through these examples in 11.2.3 pretty carefully. So spend a lot of time here on page 334. Oopsie, what did I do? Oh, I'm back. Okay. 11.2.4 is a nice theorem. It says if K is compact, then K is closed and bounded. And I would read through the proof of that. And 11.2.5, the Heine-Borel theorem, goes the other way. A subset K of R is compact if and only if it is closed and bounded. So when we're dealing with R, compactness, this thing about open covers, just means that we're closed and bounded. And we've already seen a couple of places where closed-bounded sets have some pretty special properties. And in general, a lot of those properties hold for compact sets if we're not working at all. Your book ties it together with a theorem, 11.2.6, which just ties together the Heine-Borel theorem with the Bolzano-Weierstrass theorem, and this is a cool characterization about compact sets. The reason that your book is kind of pointing out some of these characterizations is that some of these things will hold even when we're not dealing with sets in R, so when you're dealing with more complicated settings. So that kind of ties together 11.2, and that's your reading for the week.